Hello, this is Tanvir Farouk, and this is my Plus 10 talk on the future of combustion and fire safety in space. I am an associate professor in the Department of Mechanical Engineering at the University of South Carolina, Columbia campus, and my background is in combustion and plasma and reacting flows under the influence of electric field. The basis of these Plus 10 talks are to predict out the next 10 years in your area of research. And since it is trying to extrapolate the research envelope for the next 10 years, there's a chance that I could be completely wrong. But nonetheless, I'll try my level best to give an idea of what might happen in the next 10 years based on the current trends in the research areas in combustion. Even though combustion research has been going on for over multiple decades, it is of critical importance since 80% of the world energy is converted by combustion. The current trends are that we want to achieve higher efficiency, have less emissions or less pollutant emissions. We want to have fuel adaptability of these different combustion engines. As a result, the current trend is that we are pushing these combustion systems towards near limit conditions. So higher efficiency, next generation advanced engines using alternative fuels and operating at extreme conditions or near limit conditions is the key to achieve increased energy sustainability as well. The challenges in combustion research is therefore to develop a fundamental understanding of combustion kinetic process or combustion chemistry, and dynamics as well. And this should encompass from molecules towards engines. So we should go from the smallest of scales and then go to application relevant designs. There is also need of high fidelity predictive models, which actually would guide the next generation of innovative combustion technologies development as well. So where does space fit into this equation? So microgravity and low gravity combustion is critical for manned and unmanned space missions. NASA's next level of directives, which involve Lunar Gateway, Artemis, Deep Space Transport concept for Mars missions, all to an extent involve long duration space flights. So for these long duration space flights, it is important that we have efficient in-space propulsion systems that allow us to achieve these long duration space flights. We should also have efficient resource recovery system, for example, water recovery from wastes. Um, In-space power generation is also a key. Since we are also talking about long duration space flights, spacecraft fire safety starts to become an important factor as well. For many of these long duration space flights, a larger quantity of propellant will be carried. Also, propellants are required to some extent for the return flight as well. So, spacecraft fire safety tends to become an important factor in the global scenario of things, and that involves combustion process as well. So there needs to be ways how we can efficiently extinguish fire if they are generated under these spaceflight conditions. One of the key findings from microgravity combustion experiment was cool flame phenomena, which was discovered in 2012 under the FLEX program, where droplet combustion experiments were conducted on board the International Space Station. And since this discovery, there was a resurgence in cool flame research to obtain fundamental understanding and insight, which would allow using these cool flame burning behavior under engine relevant conditions, or how we can sustain long duration cool flame behavior under application or engine relevant operating conditions as per se. So I mean, premixed cool flame was first discovered by Davy in 1817, and then there was a significant period of hiatus uh, till 2000, where the premixed cool flame was discovered under microgravity combustion in 2000 under the NASA spatial program. Um, then there were some ground-based experiments that were conducted at Tohoku University to further probe these pre-mixed cool flame behavior. And then in 2012, the cool flame behavior for droplets was discovered under the NASA program, which is currently now driving a lot of those the ground-based experiments or fundamental studies that are being conducted to understand this unique combustion behavior. So where does cool flame fit? Okay, so in terms of application. So since the experiments that were conducted on board the ISS were more fundamental in nature, new engines and are targeting for higher efficiency and low emissions. So two of the designs are homogeneous charge compression ignition engines, or HCCI engines. The other one, which is a newer class, is the reactivity controlled compression ignition engines, or RCCI engines. And both these engines, to an extent, use this cool flame burning behavior to achieve the high efficiency as well as low emissions. So fundamental understanding from a microgravity experiments are feeding towards these engine relevant applications to achieve these higher efficiency and low emissions using this novel combustion behavior. To achieve higher efficiency, the current trend in combustion research is to operate systems that perform under very high pressure condition. And to some extent, they are pushing the pressure to a near limit or supercritical pressure condition as well. So as the pressure is increased under those near limit conditions, a lot of the fundamental information is missing, and there is a tremendous amount of knowledge gap in terms of how do the reaction rates behave, are the current understanding of reaction rates applicable or can they be extrapolated to these high pressure conditions. How the mixing will take place at this supercritical condition or under the extreme high pressure. And also when we talk about multiple different fuels or blends of fuels under these high pressure conditions, how does preferential vaporization of a liquid fuel behave? That is also key to know to dictate what kind of combustion behavior might take place. So we want to achieve higher efficiency, and for that reason we want to operate at a higher pressure. But then there are quite a bit of fundamental understanding that's missing that can guide us to achieve these technological development or technological milestones. So a lot of challenges that are still in place, a lot of unknowns. There should be quite a bit of research thrust directed in these areas, and which will allow us to obtain those fundamental understanding and then march forward with new technological developments or new application oriented design. So the new generation who are working in this area, this is still a pretty research rich area to dive into. Thank you.